All right. Welcome back to Chem 151. We're going to kind of move ahead into Chapter 7 here. And Chapter 7 is going to focus on electron structure, basically, inside of atoms. So we've talked in the past about the structure of the nucleus, and we've mentioned that there are electrons in there, and we've focused on electrons in terms of evaluating charge. But what we really want to start to think about is sort of the underlying structure of the way electrons are organized in an atom. That's going to give us a lot of useful information about how things like bonding happen, and that's going to help us build up our knowledge of chemistry and structure of molecules that we'll start to get to in the next chapter as well. Now, the story of kind of piecing together what's going on inside of an atom really starts with the way light interacts with an atom. So we want to start first about understanding some of the properties of light and the way we can relate some of those properties, like what is the energy of that light, what is the frequency and wavelength of that light, because light is primarily, and in most cases, it's best to think of light as a wave. There are certainly situations where light acts more like a particle, but for the most part, it's going to be this wave nature of light that we are going to focus on. So, got a couple diagrams here to show first. So, basically, we can most appropriately think of light as a wave. There's a repeating structure here, and one of the key properties here that we'll use to describe the nature and properties of light is the wavelength. So on the diagram here, it is the distance from the crest of the wave to the next crest of a wave. You could define it by any related points. You could go by trough to trough. You would get the same value for wavelength for the wave. So wavelength is the way we will usually describe light. Now, there are other properties that we'll want to compare wavelength to, frequency and energy in particular, right? But often it's wavelength that we use to define different types of light. And light is actually this broad range of different types of electromagnetic radiation. So the second figure here is sort of a diagram that shows many of the different designations within light based on the different wavelengths. So visible light, what we might normally think of when we say light, is kind of toward the middle of this range. The wavelengths of visible light are between about 400 nanometers and 700 nanometers. The 400 nanometer side being violet light, and the 700 nanometer side being red light. And we'll talk a little more about how the color varies in between with changes in wavelength. But in the larger diagram, to the longer wavelength side, which we'll see in a little bit is lower energy, we have infrared light, which essentially is the type of energy given off by hot objects as their surroundings are cooler than them. So infrared goggles, for instance, can pick up infrared light, and that's why you can see maybe an animal that is in a cooler surrounding when you use those infrared lights. Even lower energy are radar, the radar section of the electromagnetic spectrum, and radio and TV waves, and some of the waves associated with AC circuits. Right? Radar is kind of interesting because the primary use of radar is because it is so much lower energy, it generally just bounces off whatever it comes in contact with, so it doesn't interact with matter particularly well. So you shine it up in the air, it hits an airplane, and the light bounces off that airplane, it comes back to the station that sent the beam in the first place, and you can detect that light bouncing back. So there's a lot of interesting kind of material science and chemistry in designing materials to absorb these radar signals. In a stealth plane, for example, you want that radar signal to actually be absorbed by the plane, so there's no signal sent back that would help someone locate that aircraft. To the higher energy side, again, this would be lower wavelength. We'll see mathematically those relationships in a little bit. Higher energy is ultraviolet rays. This is one of the reasons why being exposed to too much ultraviolet can be dangerous, is because the extra energy of that light can actually start to damage the structure of materials in your skin cells, the DNA, the proteins in your skin cells, right? It's also what gives you a suntan by changing the structure in some of the pigments, or gives you a sunburn if you're out for too long. But repeated exposure to ultraviolet rays can have some bad effects. Even higher energy are things like X-rays. We may be familiar with X-rays from the medical usage. Right? X-rays will basically, they're energetic enough, they'll pass right through some of the softer tissues like muscles and the fluids inside your body. They're only stopped by the denser tissues like the bones. So you can use X-rays to kind of visualize bones inside of your body. And then even higher energy here and shorter wavelength would be gamma rays. So gamma rays are often associated with radioactive decay and radioactive fallout, that sort of thing. In comic book movies, gamma rays are what turns you into the Incredible Hulk. At least that was in the original comic book. I don't know about the kind of reboots of the Avengers. It seems like there's a little more going on there. But you do see this kind of energetic light coming out of the chamber when Captain America got transformed. And some of that was still related to that idea of gamma rays that kind of came from the original comic book. Okay, some definitions here. Wavelength of the light waves is abbreviated by the Greek letter lambda here. So that's something you'll want to get used to. When you see this symbol, you want to think, okay, that's the wavelength of the light. This is the distance between two adjacent peaks or troughs in that kind of cycle of light that we looked at. The first thing we want to think about relating the wavelength to is the frequency of light. So frequency is abbreviated with the Greek letter nu. So pretty close to a V, but there's a little kind of swish in there. This is not quite a V, it's the Greek letter nu. So if you were kind of phonetically spelling that, it's N-U is how you say that. The frequency is the number of complete wavelengths or cycles of light that pass a given point each second. So the longer the wavelength, the fewer times a complete wavelength will pass the point. The shorter the wavelength, the more. So there's an inverse relationship here. And this inverse relationship is related to how fast the light is moving. Well, light moves at a constant speed. Now, technically, this is the speed of light in a vacuum. Light may travel a little slower through something like air or water, but this is the speed we're going to use when we're doing this calculation. So in this case, since the speed of light can be treated as a constant, in fact, this is pretty fast, 3 times 10 to the 8th meters per second, right? This constant will help us relate these two quantities we've discussed so far, the frequency of light and the wavelength of light. So if we think about this, if we take the wavelength, for example, the wavelength is measured in distance units. So we could measure the wavelength in meters, right? And when we're doing a calculation, it is particularly common to measure the wavelength in meters because the speed of light is usually given in meters per second. Depending on the type of light, it may be defined by another measurement. Visible light, for example, we mentioned already, is usually thought of in nanometers for wavelength. Well, if the wavelength gives us meters, now the frequency up here, right? Waves or cycles that pass a point each second. The units up here are cycles per second. And what we usually do is we leave out the cycles part of it or the wavelengths part of it in talking about frequency. And we just report frequency units as inverse seconds, 1 over second. Now, you'll also see the term hertz. 1 per second is also a hertz, which is another unit we might see for frequency. But similar to molarity, you kind of want to know what's hidden underneath the term hertz. That would be 1 per second or inverse seconds, seconds on the bottom of the fraction, however you like to think about it. But using hertz makes it hard to cancel out your units. Using inverse seconds here makes it a little easier to cancel out your seconds. If we take the wavelength and we multiply by the frequency units are 1 over seconds. Right? Notice that would give us meters on top, seconds on the bottom. That's exactly the units associated with the speed of light. So wavelength times frequency would need to equal the speed of light. We can, of course, rearrange this equation depending on which of the two variables we are trying to evaluate. The frequency is going to be equal to the speed of light divided by the wavelength. The wavelength is going to be equal to the speed of light divided by the frequency. Okay, now we want to practice these a little bit, right? And then we'll get into the relationship to energy a little further down this second page as well. But the video is getting to the point where I need to stop it, so we'll stop there and we'll pick up in the next video.